Hi everyone and welcome to this, our very quick jaunt through the general cubic function. Now, I have to say, if you are waiting for the kettle to boil to have a cup of tea while watching this, I really think this lesson will be finished before the kettle even starts. So let's time this. If I can get this done in less than 3 minutes, life will be fabulous. All right, so recap. Well, we've met cubics before. All right, they are actually pretty funky. And there is my funky monkey. They have a number of interesting properties, and this video literally is about listing those properties. Nothing more, nothing less. There's not too much else we can do about them other than sketch them, transform them, and sort of read off about them. So, funky property number 1. Cubics may cross the x-axis in 1, 2, or 3 places. Well, what do we notice? Here is the standard cubic, y equals x cubed. And how many places does it cross in? Oh yes, it crosses in just the one. Here we have x cubed minus 2x. Now notice there's no constant term there. We don't always have to have a constant term at the end of this. But what do we see? We see that this crosses in 1 and 2 and 3 places. All right, oh, that's funky. What about this one here? Different. So that's just one place again, which looks slightly different from the y equals x cubed. But because we have a maximum here and a minimum here, this minimum here obviously isn't below the x-axis, so we only have that one crossing point here at -2. And then this is an example of what we call effectively 2 crossing points. Now this one here, which just touches the x-axis, is what we call a repeated root, okay? And in this situation, it's quite funky in the way that we write that, but I'll talk about that in just a second. All right, so let me see. What do we say here? So there was 1 crossing point. There are 3 crossing points there. This is another example of just the 1 crossing point that's not a standard cubic. And this one here has 2 crossing points. What we've also got to know, and this is really important for cubics, is that they can have 0, 1, or 2 turning points. Now, what does that mean? Well, in this situation here, a turning point is defined as a point with 0 gravity. 0 gradient. 0 gravity, that's a whole new movie. All right, so 0 gradient. At this point, 0, there actually gets to a point that if I draw a horizontal line through it, take a tangent to the point at when x equals 0, I would find out that the gradient there is equal to 0. Likewise, at a maximum or a minimum, if I was to draw a tangent to that point there, or in fact that point there, I would find out that my gradient is equal to 0 at both points. Right, so this one here then has 1 turning point. This one here has 2 turning points. So where is there an example of 0? Well, let's just check. Is it this one? No, that's got 2 turning points. And this one here also has 2 turning points. Well, actually, if we scroll all the way to this graph here, and apologies, my screen has gone a bit darker. My battery's about to go. All right, this one here, this turning point here, with the graph y equals x cubed plus x, does not have a point of 0 gradient. Now, to be able to prove this, we need to use differentiation, which is much later in the course, right? So I'm going to rub it out. Not that it doesn't exist now, but if we were to try and take a tangent at that point there, all right, we would find that actually that is not a straight line. So in this situation, m doesn't equal to 0. My advice to you is always remember one graph, x cubed plus x, that doesn't have a 0 gradient. All right, it's very useful for later on discussions. Now, number 3, turning points do not have to be symmetrical. Obviously, as we know, quadratics are symmetrical. They're symmetrical around an axis of symmetry. But cubics are not. And it fascinates me and somewhat terrifies me, people who think that that would have an axis of symmetry, that would have an axis of symmetry. That is not the case. I mean, in this actually, with this diagram, it's not too bad. But please do not think that if you know this value here and this value here, you can find that value there just by halving it. It really doesn't work that way. And number 4, really important, repeated roots are possible with cubics. All right, it means the graph just touches the x-axis at this point. All right, so we have here the equation of the curve y equals x cubed minus 3x plus 2, but we can actually write that in a different form. We can write that as y equals, so if we were to write that in intercept form, x plus 2, where did I get that from? Well, that's minus 2, so it's plus 2 inside a set of brackets. This crosses through at the point 1, so I'm actually going to write x minus 1 squared. This, when you see a squared there, means it is a repeated root, right? It just touches the curve, and we do a lot more of that in different lessons, right? And you're going to say, well, does that actually multiply out to be that? Well, let's just check. We get y equals x plus 2, x minus 1 becomes x squared minus 2x plus 1. Multiply this out now, so the first term multiplies by everything there. We get x cubed minus 2x squared plus x, and then the second term becomes plus 2x squared minus 4x plus 2, and let's just collect like terms. X cubed, that's good, minus 2x squared plus 2x squared disappears, that's good, plus x minus 4x is minus 3x, and then we get our plus 2, and lo and behold, these are in fact the same. Well, there you go. I hope that kettle hasn't boiled yet, and if it has, mine is milk with 2 sugars, please, but a cup of tea, not coffee. Coffee this time of night makes me somewhat hyper. Well, there we go, ladies and gentlemen, the general cubic function. You now know everything there is about cubics. My advice is when you get graphs of the form y equals x minus 2 cubed plus 4, you now know that that is basically a standard cubic, which is this graph here. Right, translated 2 to the right and 4 up. Yep, makes sense? All right, I'm done. Thanks very much. I'll see you next time.